Good afternoon, everyone. Today, I'm excited to present our research on LAV-ACT, a novel approach to enhancing bimanual robotic manipulation through language-augmented visual accent trunking. This work has been carried out by our team at Center for AI and Robotics at UAD, specifically at Embodied AI and Robotics Lab. My name is Dhruva Tripathi, and I'm presenting on behalf of my co-authors. In this talk, I will walk you through the motivation behind our research, the technical advancements we introduce, and our experimental findings to demonstrate the effectiveness of our approach. Let's get started. So let's begin with simple definitions. Robotic manipulation is basically refers to the interaction of robots with the physical world. This includes completing tasks such as grasping objects, opening doors, packing an order into the box, folding laundry, and so on. And many real-world tasks require the use of both hands. This is where bimanual robotic manipulation comes in. By coordinating two robotic arms, we can achieve precise and synchronized actions, which are crucial for applications in industrial assembly, surgical procedures, and complex object handling. But bimanual manipulation presents significant challenges as it requires precise alignment of both arms, sophisticated motion planning, and a deep understanding of the environment to ensure smooth execution. So these challenges basically motivate our work in improving robotic action prediction. Let us begin by formulating the problem. To enable robotic manipulation, we rely on a labeled dataset containing observations and corresponding actions. So these actions are often collected by human experts. Thus, the dataset is labeled as expert demonstrations. Observation sequence could be any input from robot sensors. For our research, it is going to be visual from cameras. So the task at hand is given a sequence of observations O1 to OT and their associated actions A1 to P. Our objective is to model the probability of each probability of action sequence A1 to T given O1 to T. So this can be done as a supervised machine learning approach where we train a policy pi that maps observation to actions. And one such policy is ACT, which is a short form for action chunking with transformers, where instead of predicting single actions, ACT predicts chunks of action at a time using a CVAE, conditional variational autoencoder architecture. So what it does is it models probability of A t to t plus k given OT times to t for some k, which is the hyperparameter called chunk size. Instead of predicting one action, it predicts k number of actions given one observation at time t. By doing this, ACT also significantly reduces compounding errors, which is particularly useful in long horizon robotic tasks where small prediction error can accumulate and lead to failure. So here's the original ACT architecture, which is, like I said previously, trained as a CVAE, meaning it learns to encode input to a latent distribution, and then using a sample latent variable, decode them into meaningful action sequences while incorporating a probabilistic structure. So the objective during training is to maximize the log likelihood of correctly predicting expert demonstrations. Logarithm is used because probabilities of action sequences can be very small. While training, two losses are used: reconstruction loss and KL divergence, which is the same as in the standard VA architecture. So the reconstruction loss is to ensure that the generated action sequence matches the expert demonstration as closely as possible. The KL divergence, which is also the regularizer, is used to regularize the latent spaces of the encoder. Basically, the KL divergence ensures that the learned latent variable follows a Gaussian prior distribution. Why a Gaussian prior distribution? Because using a prior helps improve generalization and prevents the model from memorizing specific examples, basically. But there is limitation within the ACT framework. One of the primary drawbacks of ACT is its reliance on visual observation, and the model depends on visual input only to predict actions without incorporating any additional contextual information. such as language or semantic cues. This can be problematic as visual input alone could be ambiguous or incomplete. Particularly, the ACT uses the ResNet uh, to process image. While ResNet is effective in many processing tasks, it is not well suited for complex robotic manipulation because it fails to capture the spatial and temporal dependencies, as well as it struggles with the multi-view understanding because we will be using multiple cameras in our experiment, which is essential in bimanual manipulation tasks. And because of these limitations, the system struggles with the real-time task execution, leading to lower success rates in real-world experiments. To overcome these limitations, we introduced LAV-ACT, an enhanced framework that integrates language-augmented visual vision processing for more adaptive and precise robotic manipulation. Here is the diagram of our architecture. We keep the original CVAE framework with the encoder-decoder architecture. But we changed the feature extractor, which was previously just the ResNet. So what we do is our approach introduces two key components. One of them is the Voltron encoder. Uh, so the Voltron encoder enables the architecture to incorporate both the visual and the language inputs instead of just the one, hence allowing the model to get context-aware embeddings, thus improving its ability to interpret the task-relevant information. And after we get the uh, Voltron features, we use film conditioning, a film which is used to modulate the ResNet feature maps based on the dense embedding from the Voltron extractor, meaning that our visual feature extractor is no longer static. It adapts dynamically to task-specific language cues, enhancing precision and decision making. So more on these to follow on the next slides. First, let's talk about the Voltron. The Voltron is a language-driven transformer-based representation learning model developed by Stanford. In our framework, we use Voltron to process both the previous, the current, and the previous visual frames, while incorporating the incorporating the linguistic prompts, allowing the model to capture temporal dependencies as well as the contextual cues. The architecture of Voltron, which was originally designed, consists of a multi-modal encoder for visual and language inputs. It also includes a visual reconstructor, uh, which refines image features, and a language generator, which enables task-aware linguistic representation. You can learn more about it in the paper. And Voltron is also pre-trained on large-scale video dataset paired with lessons, learning both low-level visual patterns and high-level semantics, so thus making it suitable for robotic tasks. The result is dense, context-aware embedding, enhancing the task-specific perception. We also then we then incorporate film feature-wise linear modulation, which is a powerful conditioning method that dynamically adjusts the feature maps based on external information, which for us is the dense embedding from the Voltron encoder. So the film layer here applies feature-wise affine transformation to neural network activations, which for us are the ResNet feature map. So the layer modulates the features by scaling and shifting each tunnel of ResNet features maps based on the contextual information, which is the dense embedding from the Voltron. So the output here is the feature map, but with task-specific cues to enhance decision making. So in other words, it can be understood as uh, instead of treating all visual features equally, film adapts visual features importance dynamically based on the linguistic and contextual signals. That's how it can be understood. And mathematically, it is done by two parameters, gamma and beta, as shown in this equation, which are trained as two neural networks in the architecture. And FC here is basically the resonant feature map. And yeah, the gamma and beta are learned scaling and sitting parameters, basically. So to summarize the novelty of LAV-ACT, we introduced key enhancements to improve bimanual robotic manipulation, integration of Voltron to generate multi-modal embedding, the feature-wise linear modulation condition the ResNet feature maps, thus resulting in improved action chunking for robotic manipulation. Now let's move on to the experimental results. For simulation results, we use the Mujoko simulation environment that is used in the ACT paper for direct comparison with the ACT. And the results demonstrate that our model consistently outperforms the ACT framework across all tasks and solve stages. Specifically in the cube transfer task, uh, our model achieves a notable improvement in the lifted substage with 16% increase from 60% to 76%. Additionally, in the transfer substages, substage, we see a 12% improvement from 50 to 62% under the same training conditions. For bimanual insertion task, we have the similar significantly high improvement. For example, in the insert substage, the success rate increases by 19% from 32 to 51%. And for a real world setup, which is also something that also later in this video below here, we use 2x arms in our lab and perform bimanual coring. Experiment shows that our model outperforms the ACT by a fine margin. In bimanual coring task, our model achieves uh, higher success rates with improvements ranging up to 13% increment, as seen in the lifting among substages. We also tested both the models on single arm coring. Our method increases the success rate by 9% in both pick and pour substages to 80% compared to 70% when using the temporal aggregation. So now let's look at the VD demonstration of the bimanual coring. That was This is the real time. This is the real time feed of the tasks that are being carried out by two robotic arms in the lab. So you can see there is perfect synchronization. The left arm waits for the right arm to pour the item with the cup. So hence, our work on LAV-ACT demonstrates the power of integrating language-driven representations with visual perception to improve bimanual robotic manipulation. We see significant improvements in robotic manipulation, particularly in bimanual tasks, with experiments showing up to 13% increase in success rates for complex actions such as pouring tasks. This research also demonstrates that enhancing visual feature extraction leads to better task execution. And in terms of future research directions, first one would be basically to develop better feature extractors to further improve visual linguistic integration for even more precise robotic perception. The second one would be include more modalities in addition to language and images, such as tactile feedback and depth information, which could lead to even better performance. So moving forward, these improvements will help make robotic systems more adaptive, efficient, and capable of handling real-world tasks with greater precision. Thank you. Here is our website if you want to learn more about the research.